Hi, let us discuss about Jacobi method and Gauss-Seidel method. Like these are the iterative methods to solve system of linear equations. Okay. Before that, we should know what is a diagonally dominant matrix. Diagonally dominant matrix. So when you take a square matrix, we say that matrix is diagonally dominant when you know the diagonal value in a row. The diagonal value is always greater than or equal to sum of the other entries in that row, that is aij, where j equal to 1 to n and j is not equal to I mean, you take this matrix 3 1 2, or okay, let me take 4 0 5 1 0 3 6. If you look at this matrix, the diagonal entries are 3, 5 and 6. Now in the first row, if you look for this condition, that is 3, the first element A11, which is 3, and sum of the rest of the entries in that row is actually 1 plus 4, but here the diagonal entry is not bigger than the sum. So here this is what happens. So now this matrix is not diagonally dominant. But when it comes to the second row and third row, it is fine. That is 5 is the middle value and sum of the rest of the entries is equal to 1. So 5 is bigger than 1 and 6 is bigger than 0 plus 3. But for the second row and third row, there is no issue, but there is an issue with the first row. So this is not diagonally dominant. So if you want this to be diagonally dominant, you change the first row. So you keep something else so that the first element is bigger than sum of the rest of the elements, because it is the first row. If it is a second row, you look for the second element. If it is a third row, third element. Okay. So let us see example of a diagonally dominant matrix. 5 1 1 negative 1 3 let me take 0 and 1 2 4. Now this matrix is diagonally dominant. Why? Because you can see 5 is bigger than this sum and 3 is bigger than, when you take sum, we are taking the absolute value. Absolute value of negative 1 is 1. So 1 plus 0, and which is smaller than 3, and 4, which is bigger than 1 plus 2. So this matrix is diagonally dominant. Okay, and moreover, this matrix is strictly diagonally dominant. Why? Because you got a strict inequality here. Okay, it's so nowhere it is equal. Like A11 is strictly greater than sum of the rest of these two entries. Similarly, A22 is greater than modulus of this is modulus of A. I should take 21 plus modulus of A23. This is all. Okay, and see, if you want the iteration process, whatever you are going to apply in Jacobi method or in the Seidel method, if you want that to be convergent, definitely the matrix should be diagonally dominant. Okay, or you can start with a symmetric matrix which is of positive definite. So let us see what is the Jacobi method first. And it is very easy. Okay, so it is very easy to understand and solve a problem as well. Let's say you are given with some set of linear equations, n equations with n unknowns, and let me write those equations. That is a11, yeah, this is the linear system we have, a11 x1 plus a12 x2 plus and all. I mean, so n equations and n unknowns are given. So here you try to arrange this linear system in such a way that this is diagonally dominant. Okay. So now once if you arrange it from the first equation, you write what is x1. So to get x1 from the first equation, you keep x1 here and you send rest to the other side. So when you send rest to the other side, negative summation, you can write it as a1j, where j is from 2 to n into xj, and here you have b1, so b1 minus of, and here you have a11, so you try to divide with that, 1 divided by a11. So this is what actually x1 from the first equation. Now from the second equation you can obtain what is x2. Okay, so b2 minus of summation j equal to 1 to n, and here j is not equal to 2 into a to j xj, and here you have a22 divide with a22, so this is a22 multiplied with this. And if you write a generalized formula for xj equal to, what is it, 1 by aii, sorry, let me write xi, so xi is 1 by aii into bi minus summation j equal to 1 to n, where I not equal to j, into I have a ij into xj. So this is how we obtain xi's. Now what we'll do is, we got an iterative formula. So the iterative formula here is, we'll take this to be the value in the k plus 1 step, and this is the value in the kth step. Okay, so here first we'll start with initial approximations, that is when xjk, which is 0. It means, initially we'll take x naught y, sorry, we'll take x1, x2 and so on xn, we'll take all of them to be equal to 0. Okay, so by substituting these xi's in this formula, we'll obtain what are x11, it means what are the numbers after first iteration, and so on xn1. Okay, fine. So let me explain with a problem so that it will be easy. Now see here, so this is the linear system you're given with. So we'd like to solve this linear system with Jacobi iterative method. So what we'll do is, from the first equation we'll write 2x equal to 4 minus y. We keep x here and send rest to the other side, that is y 4 minus y. From this you can see what is x. X is nothing but 1 by 2 into 4 minus y. Okay, and next from the second equation you can write what is 2y, that is 5 minus x. So from this, y equal to 1 by 2 into 5 minus x. You can clearly see that the quotient matrix here is diagonally dominant. See, if it is not diagonally dominant, we'll see what wrong happens here. I'll show you that. So now let me take it as an iterative formula. Here you write k plus 1 and k plus 1, and here the values at the kth step. So first I'll take, when k equal to 0, I'll take x naught, sorry, I'll take x to be 0 and y to be 0, and these are what we call x naught, y naught. Next we'd like to find x1 and y1 using those formulas. What is the formula for x1 here? So we find this x1 and y1 using these iterative formulas. So let us write the formula first. X1 equal to 1 by 2 4 minus y naught, and y1, this will be given by 1 by 2 into 5 minus x naught. Now you substitute 0 and 0 here, you'll get 4 by 2, 4 minus 0 by 2, which is 2, and similarly this is 5 minus 0 by 2, this is 2.5. But instead of writing this way, it is better to write a table so that it will be easy. So I'll write the iterative values here, xk and yk here, and where k here. Okay, when Okay, so let me write when k equal to 0. So in the first step, what is it? What are the initial values you are taking? So that we need to write. Initial values, we are assuming it to be 0 and 0. This is the initial guess. Okay, so when k equal to 1, so we need to calculate x1. We know x1 is nothing but 4 minus 0 by 2, which is 2, and y1 5 minus 0 by 2, that is 2.5. Similarly, next you need to calculate x2, that is 4 minus x1 is 2 by 2. Am I correct? Sorry, it's not x1, it is actually 4 minus y1 by 2. y1 is actually 2.5. So 4 minus 2.5 by 2. So this we need to calculate. And what will it be? 1.5. So this will be 0.75. So similarly, you can calculate what is y2. This is 5 minus x1 by 2. So this is 5 minus 2 by 2, that is 1.5. Okay. So if you proceed in this way, you can get the value when k equal to 2. So when k equal to 2, what is x2? x2 and y2. Sorry, not x2. This is what k equal to 2, and this is actually k equal to 3. x3 and y3, and when k equal to 4, we get x4 and y4. No need of writing x4 y4 all, because you are anyway here you are mentioning that xk and yk, so you can directly put the values here. Okay, so I have calculated these values, and let me put it here. So at third step we got 1.25, and whereas this one is 2.125, and at the fourth step this is 0.938, and this is 1.875, and next 0.63, sorry, it is not 0 point, it is 1.063, and next 2.031, and next 0.9, next 1.96. And if you observe that this guy converges to 1, whereas this guy converges to 2, and that is what the actual solution of this system. When you substitute 1 here and 2 here, 2 plus 2 4, and 1 plus 4 5, so 1 comma 2. So now this iteration process converges to 1 comma 2. So suppose if the quotient matrix is not diagonally dominant, then what happens is this, whatever sequence you are getting here, it will not be convergent. Okay, so this is what Jacobi method. Okay, now let us look at another method which is called Gauss-Seidel method. Here the only difference is in Jacobi method, you are calculating all xk's, then you are substituting, you are substituting all these for xk plus 1 and yk plus 1 and all. But in Gauss-Seidel method, suppose if you get the new x1, the new x1 we will use it to find the new x2. See here you got the x2, right? Here you got x1. Once if you get x1, like to calculate y1 here, this involves x0. Okay, we are using x0 here, but in Gauss-Seidel method, here itself we use the previous value, that is x1. Or let me solve a problem, then it will be clear. Why this? Let me solve the previous problem itself. That is 2x plus y equal to 4 and x plus 2y equal to 5. Now Now this is the method we'd like to apply, Gauss-Seidel method. So the procedure is same. You need to write 2x equal to 4 minus y. From this you write what is x. X is equal to 4 minus y by 2. And here 2y equal to 5 minus y x. From this y equal to 5 minus x by 2. So in both methods this is common. Okay. Next we are going to write an iterative formula. So first we'll take the initial values to be 0. X naught and y naught, we'll take them to be zeros. Next. Now we'll write formula for x1. x1 is 4 minus y naught by 2. So let us calculate x1 here. This is 4 minus 0 by 2, which is 2. Okay. So now I got a new value of x1. Okay. Now to calculate y1, we need to make use of x, right? So now to make use of x, either, there are two chances for you. One, x naught. Another one, here you have a new updated value. So instead of using the old value, so we will use an updated value here. Okay. So now y1 will be 5 minus x1 by 2. In Jacobi method, what we are doing? We are using x naught only. But here we are using x1. So now let me use the new value, that is 5 minus 2 by 2. So that will give you 1.5. Okay. Now let us calculate x2. So x2 equal to 4 minus 5 by 2. That is 4 minus 1.5 by 2. That is equal to, you'll get 2.5, and 2.5 by 2, that will give you 1.25. Okay. Now to calculate y2, so that is 5 minus, we don't use x1, we got an updated value, so we'll use x2 here. So that is x2 by 2. So that is 5 minus 1.25 by 2. So this is what we do in Gauss-Seidel. Okay. Let's see one more problem. So first let us solve this problem using Jacobi method, and later we'll do it using Seidel method. So first what you have to do, you have to arrange these equations in such a way that the coefficient matrix is diagonally dominant. And next, first you have to write what is x from this equation. So x equal to 1 by 10, or let me take a step. X equal to 10x equal to 9 minus y plus z. This implies you get x equal to 1 upon 10. This is 9 minus y plus z, right? Similarly, you can see what is y equal to from the second equation. Be careful. 1 upon 10, this is 24 minus x minus z, and from the next equation you can see what is z. 1 by 10, this is 31 plus x minus y. But if you observe that this is the system whose solution is 1, 2, 3. That is how I have taken. If you substitute x equal to 1, y equal to 2, z equal to 3, you will get these values 9, 24, 31. But let us find its solution using these two methods. One Jacobi, another one Seidel. So for Jacobi method, what you have to do, for two methods, the same thing. K equal to 0. So first let me do it for Jacobi. So here I'll write k, and here I'll write xk, yk. And there are 3 here, so zk as well. So when k is 0, we'll take the initial values to be 0, and you substitute, at the first step, you substitute x0, y0, z0 in these equations. From this you'll get what is x, y, z. Okay. So if you calculate them, let me calculate what is x1 first. x1 it doesn't matter whether you write it as a suffix or prefix. So x1, that is 9 minus 0 plus 0 by 10, so that is 0.9. okay, so x1 is 0.9. next, what is y1? y1 is 24 minus 0 minus 0 by 10, this is what y1, and this is what 2.4. so y1 is 2.4, and similarly you can see what is z1, that is 3.1. Suppose in Gauss-Seidel, what do we do? So here we got x1. Now to calculate y1, we'll use the x1. It means here we write y1 equal to 24 minus 0.9 minus 0 by 10. This is what we'll do when you apply Gauss-Seidel method. It means we'll use the updated value. Okay. And similarly, if you look at the second step, in the second step, so I have done it in Excel sheet. Okay, so here is so here I have written the formula. So these are the values in the first step we got, and in the second step this, in the third step this, fourth step, you see. So from the 8th step onwards, it exactly converges to the solution. At the 8th step, it converges to the solution. That is 1, 2, 3. Okay, so this is what in Jacobi method. So in Gauss-Seidel method, you could see. So this is the Gauss-Seidel method I applied here. You see, earlier you got 2.4 here, 3.1 here. But here in Gauss-Seidel we got 2.31, 2.951. Why? Because to calculate y2, we use the updated value. So we used updated value here. So this was calculated like this. y1 equal to what is it? It's actually 24 minus this value 0.9 minus 0 by 10. That is what. And how we got this guy? That is z1 equal to 31 minus. Now we use the updated values again. That is x1 minus y1 by 10. Maybe I should look at yeah, that is minus and minus only. So here we have to substitute 31 minus 0.9 minus the updated value of yi, that is 2.31 by 10. So this will give you this guy. Okay, so this is how we calculate. But since you'll not have a system in the examination, so you should bring your calculators and you should do this work with a calculator only. Okay, so you can see, wow. So in the Gauss-Seidel method, you see in the 5th step onwards, it started remain constant and it converged to the solution. Whereas in Jacobi method, it converged at the 8th step, but here it did at the 5th step. It means the Gauss-Seidel has faster rate of convergence than Jacobi method. Okay, and there is another method called SOR, successive over approximation method. Okay, so that is actually a modified version of this Gauss-Seidel only. So there we give some weightages. So with that weightages, what happens is the rate of convergence becomes faster compared to these two methods, Gauss-Seidel and Jacobi. So if you compare the rate of convergence of the methods, you can see first Jacobi converges very slow, and thereafter Gauss-Seidel converges faster compared to Jacobi, and compared to Gauss-Seidel, SOR converges much more faster. So this is what when you compare the rate of convergence. and these are the three iterative methods. I mean, we use it to find the system of solutions of a system of linear equations. Okay. And let me show you what is successive over relaxation method here, SOR method we call. So this is what. See, if you look at this formula is same as the Gauss-Seidel method. See, in the Gauss-Seidel method, you try to understand, there is nothing difficult here. Xk plus 1 is b1 minus of, you see this is xj, you're going up to I minus 1. Up to I minus 1, we use the updated value till that step, and after that the previous ones only. Okay, why? Because these are not yet updated. Why? Because this is ith one. Okay. So in SOR method, you are taking the same formula till here, but here we are taking a weightage, some w. We are introducing some w here, which is in between 0 and 2, and we are adding one extra term here. Okay, so this is what successive over relaxation method, right? I hope you understand how to solve problems using Gauss method, Jacobi method and Seidel method, Gauss-Seidel method. Okay. And let me know if you have any questions or if you need some more clarity on it. Okay. Bye.